Hey, Carly.
Hey Wade, today we're going to talk about the multiplication rule.
Awesome. What's that?
So, the multiplication rule is basically something that we can use to figure out the probability of multiple events happening at the same time. So, I always like to start with an example. So, I'm going to give you the Linda problem. Have you ever heard of the Linda
I
problem?
haven't. What's the Linda problem?
Ooh, okay. So, it is a classic problem in probability, and I'm just going to give it to you and see what you say. Linda is 31 years old, outspoken, and very bright. She majored in philosophy and participated in social justice movements in college. She was also active in anti nuclear demonstrations. So the question is, which of the following is more probable? So the first thing is that Linda is a bank teller. And the second thing is that Linda is a bank teller and a feminist. So, Wade, based on what I just said, which one do you think is more probable?
So in both cases, she's a bank teller.
Yes.
And only the second case, she's also a feminist.
We have the second condition. We have the and feminist.
So I think it's very unlikely she's a bank teller. I don't have any evidence to support that. So maybe it's only 10% chance. But you said she's in the social justice movement. She's probably more likely a feminist than a bank teller. Maybe she's 50% chance she's a feminist. So option number two.
That is what most people would say for this question. When you ask thousands of people the Linda problem, almost everyone says option number two, because from what I described, it sounds like she would be a feminist, right? But actually, because of the multiplication rule, option number one is more probable.
So can you explain?
Yeah, let's think about this before we actually figure this out in terms of the Linda problem. Let's think about it with something we know and love, the die.
Yeah.
So let's just say I wanted to know what's the probability, and I'm going to use this probability notation, P parentheses 1. So this is read as the probability of getting a 1 is what? Wait, if I roll this die, what's the probability I get a 1?
So it's a six-sided die. So
Mm-hmm.
one out of six options.
Exactly. And I just didn't get one, but 1/6. Um, probability of any number is 1/6 with rolling a die. But if I said, what if I roll twice? What if I get a 1 and a 2? This is a little more complicated to figure out. We actually have to use something called the multiplication rule. So for independent events like rolling a die, the multiplication rule says that the probability of any two events, events A and B, we can figure this out by basically just multiplying the two probabilities together. So by taking the probability of A times the probability of B. And this works for independent events like rolling a die. It also works for flipping a coin, and we can think of other examples where it would work as well. But so you just told me that the probability of getting a 1 is 1/6, right?
Yes.
And means to multiply.
So what do you mean by one and a two? Am I rolling two separate die here?
Ooh, that's a good question. So you could roll, it actually doesn't matter. I could say I'm rolling the first time and getting a 1 and then rolling the second time and getting a 2. Or I could say just rolling two dice at the same time. The probability is actually the same, again, because of this multiplication rule.
But only the same if we're specifying the die. So it's a probability of the red being a one and the yellow being a two.
Yep, that looks great. So what is the probability of the yellow being a 2?
Just so it's also a 1 in 6 chance, so 1/6.
Yep, and then if I multiply these together, I actually get 1/36. So we can see here that the probability of both things happening is less than the probability of the first thing happening. And because probability ranges between 0 and 1, then this multiplication rule, with the more conditions we add, the smaller that probability is going to be. So with the Linda problem, I think, Wade, you gave me some numbers. You said, let's just say the probability that she's a bank teller is 10%.
That's just an estimate, but
That's
I
an
think it might be
estimate.
good.
Yeah. And then what about the feminist?
I thought it might have been about 50-50.
Okay, so you thought 50/50. So this was 10%, this was 50. We know the probability of her being a bank teller is 10. We're assuming it's 10%. And then if I wanted to find the probability that she's a bank teller and a feminist, given these percentages, given that they're independent events, I would just multiply these two probabilities together. So for 10%, I'm just going to write that as 1/10. For 50%, I'm going to write that as 5 over 10. And I end up getting, what do I get, Wade?
So multiplying top 5 over 100, which nicely is a percentage, just 5%.
Yeah, we get 5%, and that is indeed lower than 10%. So your logic was correct that the probability of her being a feminist, from what I described, seems to be higher than her being a bank teller. But because we're multiplying those probabilities together, it actually is lower than any one of them individually.
So if I chose different numbers, would have the results been differently? If there was a 90% chance she was a bank teller and only a 10% chance she was a feminist, would that change the results?
So let's go ahead and see. Let's say there was a 90% chance she was a bank teller. Let's say I said something about her loving banks, loving money, or something like that. Times, what did you say for the feminist?
Just 10%.
10%.
So now this event is the more likely event than the other event.
Yeah, exactly. So the probability that she's a bank teller would be, instead of 10, this would be 90%. And then the probability that she's both would be 9 over 100, still smaller. This would be 9%. So we actually get a different final percentage, but we still get that property that the probability of both of them is smaller than any of the individual probabilities, because 9 is also smaller than the 10% that you said for the feminist.
Anytime we have a situation where we have an and, it's always going to decrease the probability of it occurring?
Yes, exactly. And we can add more conditions as well. Let's say I wanted to know what's the probability I get a 1 and a 2 and a 3.
So I need a 1
Yeah.
and a 2 and a 3. Ooh, that's not very likely.
Yeah, exactly. I'd have to multiply that 1/6 chance. Chance I get a 1, we said, was 1/6. The chance I get a 2 is 1/6. Chance I get a 3 is also 1/6. And, ooh, what is this, Wade?
So this is going to be 1 over 216.
So this is the smallest.
So like half of 1%.
Basically, yes. And I kind of like to think about this with an example from, I guess, the current time. So like, let's say that you were doing online dating. This is maybe a slightly provocative example, but it demonstrates the multiplication rule really well. So if you're on an online dating app and you say you wanted someone who is smart, there's probably a lot of smart people, right?
50% of people, maybe.
Yeah, exactly. So you have a large pool to choose from. But then what if you say you want someone that is smart and tall? Then it gets smaller, right? And what if you want someone smart, tall, and rich? And all of these conditions that you keep adding, the probability of finding someone gets smaller. The pool that you're choosing from gets smaller. So that is the multiplication rule in a nutshell.
Awesome.